Paper that we've written on the mission architecture for a low-cost, redundant robotic rover for mapping mission areas. We've built this to try to meet the need for low-cost and highly redundant rovers to explore lunar and Martian terrain. Specifically, we've developed this version of it, along with a payload to provide mission information for mission planning on Mars. It's designed to be a very small, compact rover. I can't get that back up. In order to be able to provide high-fidelity mission mapping and sample terrain mapping and mineral analysis on Mars. So, when most of us think about revolutionary things within the last couple of years, in the space industry, when you think of new innovation, most of us will think of reusable launches. Things like SpaceX, who have launched, come a little closer, have launched and re-landed the rockets several times. However, one of the most important revolutions and innovations that have come to the space industry in recent years has been the deployment of the CubeSat system, a standard system that is able to be used by researchers and private institutions, has revolutionized access to low Earth orbit for everybody. It is much more feasible for anyone, especially people in this room here today, to be able to send up payloads into orbit to complete PhDs, necessary medical experiments, and a lot more that has been enabled by the CubeSat system. However, as we start to move to the Moon and Mars as our target, as we have seen through Artemis and through many of the space agencies here today, we should be looking to bring that same standardization to rovers and interplanetary spacecraft. We've actually been speaking with agencies and private companies here today, and all of them are looking to implement standardized ways to integrate with customer payloads in order to be able to deploy them onto other planets for necessary research. As a result, we've developed such a platform to try to begin the process of looking into that standardization, as well as provide a very low-cost solution. A lot of the components that we've been using, because we are a frugal organization, have been off-the-shelf hardware and components. A lot of issues that have been foreseen with space components is that they are using bespoke technologies that are being developed specifically for space missions. When those cost $1.5 billion each for a rover, and much more to send it to Mars. When you're using off-the-shelf components, it turns out through testing that they are not only applicable, but very useful and generally fit the bill exactly for what you might need for radiation tolerance, for being able to stand up to harsh environments like the Mars. In fact, we've actually been talking on a previous project and found out that Iceland can often be a harsher environment than Mars, apparently. That probably speaks more to Iceland than it does to Mars, though. So we've also partnered with a lot of different organizations to help us develop different and novel technologies for this. In fact, one of the last year's presentations by a Sri Lankan team called Lunabot developed an active controlled wheel system where the grousers on the wheels are actively pushed in and brought out in order to be able to reduce sinkage and slippage on the rover and actively increase efficiency of power on the rover, even though it's an actively controlled system. We developed a Trident-style sampling method, which allows us to be able to sample and perform spectroscopy on such samples on the Moon and Mars that will allow us to be able to rapidly cover massive mission areas, up to kilometers, square kilometers, in as little as a week to 2 weeks. You should be able to deploy a system of up to 50 of such rovers, which will autonomously navigate themselves around and be able to decide among themselves. An obvious advantage of being able to deploy such a large amount of these rovers is that you can have 1, 2, 5, or 10 of them just break down out of nowhere for any reason whatsoever, and you should be able to continue on as normal with your project. Excellent. So as I said before, we've been speaking to a lot of the companies and space agencies here today, and a lot of them are waiting for such a standard to be able to be put forward. It makes sense to build such a standard off of CubeSats, which are already an established standard, and we'd like to continue to bring that at a larger level to rovers and interplanetary spacecraft. With such a system, you're no longer looking at 1U, 2U, 6U, but you're looking at up to 32 and above U, and you're playing Tetris with it because you can just fill as much space as possible on the rovers. Such standards could be implemented on bespoke rovers by NanoAvionics or NanoRacks, who aren't currently looking at lunar options but could be. and easily integrated at any level, even from the 1U platform up to massive Curiosity-sized, car-sized rovers. As I was saying, navigation is done completely autonomously. We've been developing a SLAM-style system and a novel, completely virtual testing environment to be able to lower the costs of analog testing. We plan to send out these kind of robots to analog test sites such as High Seas, Chasm, MDRS, the FMARS, Flashline Mars Arctic Research Station, as well as to the Iceland team, Chill Ice, that's who I was trying to think of, in order to try and break it and develop it as much as possible. And working with analog teams massively lowers the development cost. We can basically design this for under a few $1,000s compared to NASA's rather larger budget, which I'd love to have. But as you can see, we've developed this. I know these are renders to show how the payload system works, but we've actually developed and built these systems already, and we're going through the process of testing these out in different environments before we send them off to the analog missions.